our speaker for today, uh, who is Professor Jitendra Sangwai. Professor Sangwai is currently working as a full professor at the Department of Chemical Engineering, Indian Institute of Technology, Madras, or IIT Madras. He did his PhD in chemical engineering with Professor Santosh Gupta at IIT Kanpur. Dr. Sangwai's research interest lies mainly in the field of carbon capture and sequestration, gas hydrates, and upstream oil and gas engineering. He has published approximately 170 international journal papers and 90 conference publications. With that, he has an H index of 46 and almost 7,000 citations. Dr. Sangvi has filed 20 Indian patents and 18 international patents and has graduated 24 PhD students. Dr. Sangwai has also been recognized with various awards, including the Government of India National Geoscience Award for outstanding research contributions in oil, natural gas, and gas hydrates, two national awards for the technology innovation, Society of Petroleum Engineers Distinguished Award for Petroleum Engineering Faculty of the South Asia and Pacific region, and Regional Service Award, the Young Faculty Recognition Award for Excellence in Teaching and Research at IIT Madras. The ACS Journal of Chemical Engineering Data, has highlighted him as one amongst the 25 emerging investigators. Dr. Sangwai also serves as an associate editor of prestigious journal Energy and Fuels, published by the American Chemical Society. Thank you, Professor Sangwai, for joining us. The stage is all yours.
Today's talk is primarily focused on environmentally sustainable CO2 sequestration in ocean for sustainable energy transition. So, as a title suggests, there are two sustainable terms that are coming up. How to ensure the CO2 sequestration is sustainable, and the second is that we are talking about energy transition. That is not going to happen quickly, and it will be a very slow progress. So that transition to the renewable sources also need to be sustainable. And in near future, it is expected that we will continue our reliance on fossil fuels, and therefore we want to ensure that the CO2 that is being emitted need to be captured and sequestered safely. So before I go ahead and talk more detail about this topic, just to tell you that we are working at IIT Madras on various aspects of upstream oil and gas engineering. Some of these are highlighted here. We do work on gas hydrate as a source of energy, and also we look at hydrate, as a way to sequester carbon dioxide into the subsurface, ocean sediments. We also had worked on drilling fluids and fracturing fluids during past few years. Currently, we are also looking at how the CO2 can be sequestered on the onshore formations for enhanced oil recovery purpose. And part of our research was also focused on flow assurance. So, today's talk is primarily focused on CO2 sequestration in ocean for sustainable pathways. So as we understand that CO2 emission is increasing day by day, and in last 40 years, it has increased almost to like 10 gigatons of carbon per year. From 2011 to 2050, we are expected to produce about 1100 gigatons of CO2, which need to be captured and sequestered safely somewhere. One has to understand that conversion of CO2 to value-added chemicals completely may not be possible. And therefore, you cannot store CO2 at home or industries for longer time scale. And therefore, in order to get rid of the CO2, you need to find out how to sequester CO2 in a safe geological formations. This is very important because you have to understand that the global temperature is increasing, and we need to ensure that this temperature is confined within 2 degrees centigrade in next few decades. If you look at this graph, the atmospheric CO2 parts per million is currently about close to 420 ppm in the atmosphere. Also, the CO2 emission that has increased from almost 1750 to now 2020, it has now close to about 36 gigatons of CO2 per year. And that is also expected to rise because we still use a lot of fossil fuels for all our energy requirements. So therefore, how to make this, overall strategies, carbon neutral? It is, of course, we have to switch over to renewable and something which produces less amount of CO2 into the environment. But doing that, it will take some more time. So therefore, large-scale utilization of carbon dioxide, large-scale utilization of carbon capture and sequestration strategies are very important pathways for next few decades. We are talking about significant amount of CO2 that is being emitted into the environment, and therefore efficient technologies are important to capture that CO2 from the flue gases and the atmosphere and store that in geological formation. So if you look at the CO2 emission and population, it is directly related. You know, the population has increased across the world in last 200 years, and therefore, so is the CO2 emission. So this graph shows that how the CO2 emission has increased along with the population. It has moved from Industrial Revolution 1 to Industrial Revolution 2, and then Industrial Revolution 3, where rapid urbanization took place after 1970s across the world. And now we are talking about computer technology driven industrial growth, and now we are talking about AI and data science, etc. It is expected that our energy requirement will also increase, and as we grow our population, our CO2 emission into the atmosphere will also continue to rise. If you look at the energy, if you look at the CO2 that is being emitted into the atmosphere, the energy uses is primarily contributing significant amount of CO2 into the atmosphere, and therefore alternate source of energy are important, for the mankind to sustain for longer time. So if you look at this graph which talks about the global land ocean temperature anomaly, so we can see that after 1970 the land temperature has started to rise as compared to the ocean temperature. Ocean temperature remains almost stable, however the land temperature is increasing day by day. In order to ensure that you want to control this temperature within the designated limit in next future, if you try to look at the drastic curtailment of the emission, what you could achieve is a scenario C, where you can actually reduce the temperature and control it within 0.6 degrees C or somewhere of that order. But if you cannot do that without curtailment, the annual mean global temperature will increase beyond 1.4 or 1.6 degrees C, and that will continue to rise. So these are some information that tells you that immediate actions are required, and we do not have much time. We need to capture CO2 and then, ensure that it is safely stored. So there are different pathways which are under development across the scientific community and also at the industrial level. So one can talk about CO2 capture from the point source, where you talk about CO2 capture from the power plants, flue gases. And then once you capture that, there are different pathways that can take care of algal biomass, and then you can actually convert that into the chemicals, biochemicals, etc. Then there is abiotic CO2 storage, which talks about geological sequestration or ocean sequestration. On land, typically it is done in a depleted oil and gas field or in the saline aquifers, or also it can done in the permafrost region. So permafrost region is where the temperatures are lower at the surface conditions. And the other pathway is primarily looking at the CO2 sequestration into the ocean for long-term storage. It can be done at the deep sea or the shallower environment. Now we'll look at in this talk that how one can ensure the CO2 sequestration in a very sustainable manner for long-term storage under the CO2 conditions. So this is so just to tell you that whatever the citations that I have reported here on the slide, the color which are in blue are our own work, and which are in the black is somewhere else that we have taken the information from. So this is taken from a paper published in 2018, where ocean storage was reported in a TRL2. Now it has moved to TRL3 in last few years, and more of the lab stage studies are being looked at a different levels. And it is expected that in next few years, it is possibly go towards the pilot plant level, where we can actually look at CO2 sequestration in ocean as a way to deposits large amount of CO2. So why the CO2 sequestration in ocean is something that we talk about in a very positive way. One need to understand that methane hydrates are also available in ocean, and they are there for millions of years. And that is where the mother nature has ensured to capture CO2, to capture methane, which is either produced because of the thermogenic way or because of biogenic methane. in the permafrost or at the seabed, where the hydrates of methane have been formed. Now, these hydrates are formed because of the low pressure, high pressure and low temperature conditions which are prevalent at the bottom of the sea. These hydrates are inclusion compound which forms when the water molecule forms a kind of cages where methane gas gets entrapped. This typically is a very common phenomena at the seabed. And you might know that a large amount of methane hydrates reservoirs are available across the world. And these are some of the samples which are shown here. This is how the methane hydrate looks like. So it is like ice-like compound. So it looks like an ice. And this is a solid hydrates, right? So here methane hydrates are there for millions of years without affecting the environment. If Mother Nature would not have taken care of capturing this methane in hydrate form, it would have created a lot of havoc in the earth environment because methane is more potent greenhouse gas as compared to carbon dioxide. And that is where researchers are looking at to sequester CO2 into the ocean like the way methane hydrates are there for billions of years. So before discussing further, I would like to tell you what kind of structures this hydrate forms. Now this is a simple structure one which is formed by water molecule at high pressure and low temperature conditions. So here this 12 pentagon and 12 pentagon and 2 hexagon forming a structure 1 likewise. And then there are structure 2 and structure H also reported into the literature. Primarily methane or carbon dioxide kind of gases form structure 1. Structure 2 and structure H are formed again by different gases depending upon their molecular size. Now, when you talk about the stability of these hydrates, as I said, the hydrates are formed at high pressure and low temperature conditions. The thermodynamics plays an important role. So here, this graph shows in a simple way, a schematically a pressure temperature diagram and how the stability of hydrates are defined. And I will relate this discussion subsequently for my future slides also. So here, this black line shows a hydrate dissociation curve or also called as hydrate stability curve. Here on the right hand side of this curve, the hydrates are unstable. That means there is no hydrate formation is possible at high temperature and low pressure condition. However, on the left hand side, the hydrates are reasonably stable. And then you can actually have a zone 1, zone 2, depending upon whether it is formed by ice or gas or so and so forth. So on the left hand side of this black line, the hydrates are stable and this is primarily a stable hydrate zone. Now, depending upon the kind of gases that these hydrates are formed, the pressure and temperature conditions may vary. For example, methane hydrates requires more higher pressure and lower temperature as compared to carbon dioxide. Carbon dioxide can form at reasonably low pressure and higher temperature conditions. So, how this thermodynamics is important when you talk about the stability of hydrates or the formation of hydrates in ocean. Now, before we go ahead and discuss further, again, I will revisit this phase diagram and I will show you that how this hydrate stable region relates with the carbon dioxide gas liquid curve. Now, this is you can see this black line which represent the CO2 gas liquid line, and then there is a critical point, and this red line represent the CO2 hydrate stability curve. So this is a gas for CO2 gas liquid line, and this is a hydrate stability curve which is shown by red line. Then there is a methane hydrate stability curve which is also shown here for a reference, and there is a propane hydrate stability curve that is also shown by reference. Now we'll focus primarily on the methane hydrate, primarily on the CO2 hydrate. Now you can see that at a certain pressure below this line, which is a black, the CO2 remains in the gas phase. And any condition on the left hand side of this red line represent the hydrate stability region. So for example, if you want to form a hydrate at this condition, this CO2 gas will primarily form the hydrate because the CO2 remains in the gas phase. However, at a pressure above, say this is about 2 degrees centigrade, so at a pressure close to about 4.5 megapascal and above than that, the CO2 will be primarily in the liquid phase. So any condition at this point, the CO2 will form hydrate from the liquid phase. So liquid CO2 will reasonably form the hydrates at this condition. And then as you go above than this point, the CO2 liquid will become a dense liquid, and then again the dense liquid will be predominantly forming hydrates. Now, this right hand side curve again tells you that how this hydrate stability or hydrate forms. So as I said that any line, so this is a hydrate stability curve for the CO2 hydrate, and this side is the unstable hydrate. So this is a primarily water CO2 gas or water CO2 liquid or water CO2 ice CO2 gas. Anything that is there is primarily a CO2 hydrate forming region, and that is will be in phase with CO2 liquid or CO2 gas depending upon the pressure and temperature conditions. So now going further, this is a very interesting figure. Now in ocean water, how it looks like. So if you talk about the CO2 hydrate formation in ocean water, so if you want to really sequester CO2, how it looks like. Now this is a thermocline which represents, so this is a data with respect to the temperature, oceanic depth, and this is the pressure. And this blue line that is shown here, dotted line, is the thermocline representing a sample thermocline for Gulf of Mexico. And this solid blue curve here, which represents a CO2 saline water hydrate. So CO2 forming hydrate with a saline water, and this is the CO2 forming hydrate with a pure water. And then there are other curves for methane hydrate, which I will not really focus on. But now, if you look at this ocean water, and if you want to sequester CO2 into the ocean, what one can see that, so how to read this graph? So if you look at this point P1, the corresponding depth is about 100 meter, and corresponding temperature can be read from the thermocline, which is about 292 degree Kelvin, right? So this is close to surface temperature. As you go deeper and deeper into the ocean, the temperature will decrease, right? So for example, at P4, the corresponding temperature can be read, crossing horizontal line on the thermocline, and then correspondingly reading at on the top, which is close to about 278 degree Kelvin. So generally, at the depth beyond 1000 meter, the temperature of the sea is close to 4 degrees centigrade of that order, or 277 Kelvin, right? And as you go down and down, your pressure also will rise. Hydrostatic pressure will also increase as the depth increases. Now, this point P1 represent a condition which is about 292 degree Kelvin, and corresponding depth is about 100 meter, where the pressure is of the order of 1000 kilopascal. Here in this condition, the CO2 hydrate will not form because this condition lies out of this hydrate stability zone. Now look at the point P2. It appears that this P2 lies on the left-hand side of this region, which represent hydrate stability condition. However, the corresponding temperature at P2 is about 287 Kelvin, and therefore, at this condition, the CO2 will not form hydrate. As you go down at P3, which is about 600 meter, you can see that the corresponding temperature at this zone is about close to 280 Kelvin, and the pressure is again of the order of 6000 kilopascal, which indicates on the left hand side of this blue hydrate stability zone, and that indicates that at point P3 hydrate will form. And so is the case for P4 and P5. At this both condition, the CO2 hydrate tends to form because the corresponding temperature and the pressure conditions lies towards the left hand side of this CO2 hydrate region. So therefore, one can see that a point which crosses at the thermocline, which is at approximately 490 meter from the sea surface depth, that is a point where it is expected that the corresponding pressure and temperature conditions are such that the CO2 hydrate may tend to form if the CO2 is sequestered into the ocean. Now, the CO2 hydrate density is slightly higher than the ocean water or saline water, and therefore, if the CO2 hydrate is formed into the ocean, it is expected that they will, settle down slowly. However, one has to, of course, understand various other environmental effects, and therefore, I'm not telling you that you have to sequester CO2 into the ocean, right? That is not the focus of the discussion here. However, one has to understand that how this hydrate stability looks like if you go into the sediments, subsea sediments. So that I will come subsequently, but before that, I would like to again take your attention on this pressure temperature diagram. Now in pressure temperature diagram, here I have shown you again a curve which represent your CO2 gas liquid line, and again this is the critical point for the CO2, And here the red line represent your CO2 hydrate pure water phase stability curve, and the black line here, dotted line, represent the CO2 hydrate seawater phase stability curve. This is almost closely matching here with 1.5 degree K separation. So one can look at that a condition typically that involves ocean sequestration. As I said you that you required about 490-meter sea depth. Correspondingly, the conditions represent CO2 liquid phase conditions. And as you go deeper and deeper, the corresponding conditions represent dense or compressible liquid of CO2, and therefore the shaded area, this shaded area represent a condition of a temperature which is ranging from about 276 K, which is a temperature at the sea bottom, to about 285 K, which again tells you the maximum stability at which CO2 may form hydrate, is a region where the CO2 can form hydrates in the ocean. So this is a potential zone for ocean sequestration that is shown here in a pink shaded area. And this is a condition which is shown here light green. This is the CO2 added seawater phase stability curve as is shown here, and this region is shown specifically for the CO2 sequestration in the permafrost, because in permafrost the pressures are not increases beyond certain depth, specifically corresponding to the temperature at which the CO2 hydrate may be stable, because in permafrost if you go down and down, the thermal gradient will increase, and therefore there is a certain range in a permafrost where you can form hydrate, and you cannot really have significant space to form hydrates there. However, in permafrost, if you form CO2 hydrates for sequestration, they may get destabilized in case of any seismic activities or in any kind of sudden disruption to the hydrate zone, and therefore CO2 sequestration is potentially a zone where one can look at positively. This diagram indicates a density of CO2 with respect to the temperature, and these are the line which represent at a different pressure conditions, which is starting from 70 megapascal to about 9 megapascal. When I talk about this seabed temperature, you are talking about much lower temperature, less than 10 degrees centigrade in the sea, and at those conditions, if you look at the corresponding density at higher pressures, so this is a region where you can actually look at the CO2 sequestration in the ocean. At the surface, at the sea surface, seabed, the CO2 sequestration in ocean floor in hydrate mounts are possible. However, in the deep sea, it is expected that the pressure will rise, beyond 25 megapascal. So this is a line where we talk about 25 megapascal, and at that point and beyond that, the CO2 density will increase about 1000 kg per meter cube. And technically, that at that condition, the CO2 density will be more than the seawater density. Seawater density is slightly above than the pure water, which is 1040 kg per meter cube. And therefore, at higher pressure, being the CO2 is more dense than the seawater, it is expected that the CO2 film will settle down into the ocean. And that is where a very interesting clue when you talk about the density relation of CO2 with respect to the seawater. So how it looks like when you talk about the subsea sequestration in the ocean. So this is the depth from the sea surface from 2000 meter sample curve is shown up to 3500 meter at the sea surface and beyond that. So this is a thermocline, and as you go down below the seabed, the temperature will rise, because of the temperature gradient. And this is the hydrate stability zone. You look at, so anything that is on the left hand side will shows a stable hydrate zone. Now, as you go down and down here up to this point, which crosses this thermocline, that is the region where you can actually form hydrate, because beyond that the temperature will rise, and then this temperature will not be enough to form CO2 hydrates at that depth. Typically this range of the depth is of the order of 330 to 360 meters from the sea floor, and that is called as the hydrate formation zone, HFZ. Now I will discuss another terminology which is called as the negative buoyancy zone. Now look at this diagram here. So this is the depth from the sea surface. Sample depth is taken as 3500 meter from the sea surface, And beyond that, as you go down, again, if you look at the density of the carbon dioxide, as compared to the sea depth, it increases. So this is a density on the top shown here, sample density curve. So the density increases. As I told you that, the as a higher depth, the CO2 density will tend to increase than the seawater. So seawater density is typically of the order of 1040 kg per meter cube. It again depends upon the salinity. So as you go down and down, the density of the carbon dioxide increases, and then it crosses with the seawater density. Beyond that, the density of the CO2 will be more than the seawater density, and therefore, any depth beyond that certain point, the CO2 plume tends to sink because it is heavier than the seawater. Beyond, above than that, up to 2,800 meter approximately, the CO2 plume tends to rise because these are lighter than the seawater. And therefore, if you inject carbon dioxide in a sea at a depth beyond 2,800 meter, where the pressure is approximately 28 megapascal, and then density of the CO2 increases beyond the seawater, the CO2 plume tends to sink. Now, if you go down into the subsea sediments, what will happen? That the density of the CO2 again start decreasing because the temperature will rise slowly. And as I shown here, this temperature gradient in the subsea sediment, accordingly the density of the CO2 also starts decreasing, right? So it decreases that. And this is a density of the seawater that again goes like this, because you have pore water also here in the sediments. So the density of CO2 density of water is also slightly varies here, around 140, 1040 kg per meter. So up to this point, at certain point, the density of CO2 will remain higher than the seawater density in the sediments, right? So here also the CO2 plume tends to sink. However, if you go beyond a certain depth in the sediments, the density of the CO2 will remain lighter than the seawater density, and the CO2 plume may start rise here, right? So there is a very interesting phenomena that may happen as the CO2. So if you try to inject CO2 at this point in the subsea sediments, what will happen? That the CO2 will start to rise because it feels that it is lighter than the seawater. As it comes somewhere here, again, the density of the CO2 will increase than the seawater, and again it will start sinking here in this zone. So in any condition that the CO2 plume will end up sinking up to a depth of the order of 225 meter. That depth is ranges from 190 to 225 meter. This depth is called as a negative buoyancy zone. That means it doesn't allow the CO2 to escape at the top, because the CO2 being highly dense than the seawater. Below than that, the CO2 plume will be lighter than the seawater, and it will starts rising up. So at the end of the day, the CO2 plume, CO2, whatever you are going to inject over here, will hover at this interface of at the end of this negative buoyancy zone, and that's where is a very interesting possibility of sustainable CO2 sequestration arises, because you can then expectedly store CO2 for a longer time, and even in case of seismic activity, there might be some increase in the temperature, but however here the density of CO2 will remain higher than the seawater. It will again settle down at the end of the phenomena. So how this will work out? So this is again a hypothetical injection point here shown here. So what will happen, that if you are trying to inject carbon dioxide into the subsea sediment, you have a hydrate formation zone, and you have a negative buoyancy zone. So negative buoyancy zone will not let the CO2 go into the ocean. It will actually capture for a longer time, because the density of the CO2 will be higher than the density of the seawater here, right? So CO2 plume will always come down, and this here, the CO2 plume will always try to come up. So what will happen over a period of time, the CO2 will tend to form a hydrate layer at this zone, and this hydrate, as I said, like being a solid in nature, that will also form additional permeability barrier for CO2, and will avoid its escape into the environment, seawater environment, right? So therefore, there is an additional barrier because of the gravity due to the higher CO2 density, and there is additional barrier due to the permeability, where the hydrate over a period of time will form into the ocean, and then it will actually plug the kind of complete zone for a longer time, right? So this typically happens generally 2,800 meter above the sea depth, because at that point, the density of the seawater is density of the CO2 is expected to be higher than the density of the seawater. Now, based on that, various strategies are possible in CO2 sequestration into the ocean. One is that you can form, you can sequester CO2, of course, into the ocean. As I discussed that earlier, that you can actually form hydrate beyond 500 meters, because at that point, the CO2 hydrate may be slightly denser than the seawater, and they may settle down. However, this is not recommended always. Then other possibility that you can actually, beyond 2,800 meters, you can form CO2 hydrate, and that can be like a mold, CO2 hydrate molds at the sea surface, seabed surface. Beyond that, you can actually inject CO2 into the sediments, subsea sediments. And as I discussed the concept of negative buoyancy zone and hydrate formation zone, the CO2 will remain permanently sealed into the subsea sediments because of its nature being heavier than the seawater at that specific depth. You can also consider sequestration of CO2 beyond subsequent depth, say more than 4,000 meter or 6,000 meter, where you can actually form liquid CO2 pools into the ocean, where again, as I said, like at this condition, the liquid CO2 will be again denser than the seawater. And for a longer time, what will happen, that at the surface, it's possible that the hydrate layer may form. You might have seen, in the winter in Dal Lake, for example, in Srinagar, the Dal Lake actually freezes, that the surface actually you can see complete ice, and then people even walk on the Dal Lake, that you might have seen, So that is what is also expected, that in the long run, this liquid CO2 may form hydrates at the surface interface of the seawater and this, and then they will again completely seal liquid CO2. Now, long-term storage of CO2 into the subsea sediments or even in sea is also possibly results in formation of carbonates or bicarbonates and some of the other minerals over a longer time, and more research is required in that direction. So these are some of the impact of various organic matter or clay structures that are available in the literature, and then we have collected that information and understood that some of these subsea sediments like sodium mortallite, salinity, kaolinite do impact the phase stability condition of CO2 hydrates. For example, here it is shown that organic matter in kaolinite and illicite shift the phase diagram towards sodium mortallite here. So it actually can inhibit CO2 hydrate slightly. And also, it has also been reported in the literature that organic matter in sodium mortallite clay can shift CO2 hydrate phase diagram towards promotion. So it can actually promote hydrate formation. So some of these important observations are required to further, ensure the sustainable CO2 sequestration into the ocean. So we have carried out various studies in the literature. I mean, we have published that also, and we have looked at impact of different sediments. Primarily we have taken sand of a different dimensions, and we have carried out studies using liquid CO2 at 6 megapascal and close to 3 to 4 degrees centigrade. And these are again the lab studies where we actually simulated these subsea conditions, and then hydrate formation has been looked at, understanding the impact of the size of sands that may really enhance the CO2 formation or not. So what we observed that when you look at the liquid CO2 studies at the lab scale, formation of hydrate is easy, but capturing that signature is very difficult. Primarily, hydrate formation is a exothermic process, right? So during hydrate formation, one can look at rise in temperature in the reactor. However, when you do that experiments with liquid CO2, sometimes you may not be able to capture that information, because liquid, you are dealing with liquid phase, liquid water and liquid CO2, and therefore the pressure decrease may not be that substantial in some of the cases. So we looked at some of these impact of silica sand size, and what we observed is that the number of moles of gas that is being consumed during the hydrate formation in pure water and seawater do affect the hydrate kinetics. So seawater, because it has a salt in it, and therefore it is expected that the kinetics get inhibited. So the hydrate formation in seawater is relatively slower process than compared to pure water. And of course, the what we observed is that the smaller the silica sand size, then your hydrate formation is reasonably faster than the larger silica sand, because you have more gas liquid contact area at during the course of reaction. So we then looked at understanding the hydrate formation in clay, bentonite clay, because you have clay and sands and silt sediments in the subsea condition. So some of these studies are also being carried out in our lab. And what we so this is a sample figure for some of the cases that we carried out studies, including bentonite. We varied the bentonite percentage 1%, 7% bentonite in seawater. Primarily the studies were looked at in seawater. And then we also looked at impact of surfactant, because surfactant is something that is often used as a kinetic promoter to promote hydrate formation. And what we observed is that surfactant do improve the hydrate formation, as compared to simple seawater condition. However, in the case of bentonite, the surfactant also help us to improve the hydrate formation. It increases the reaction rate. However, one can see, in different situations, when you use a bentonite, then part of the CO2 also get absorbed into the bentonite clay, and part of the hydrate also get formed. So CO2 sequestration happens primarily both getting absorbed into the bentonite clay, and also formation of CO2 hydrates in sediments or bentonite clay here. So here the CO2 hydrate formation typically observed. So this red line represent CO2 gas liquid line, and we have carried out the studies close to gas liquid equilibrium condition, because here then you can actually quickly understand the pressure decrease profile. So you can see that suddenly when the hydrate formation occurs, the pressure has drastically decreased from about 3.5 to close to 3 megapascal, and that indicates the hydrate formation. So this is the hydrate induction, and then you can actually again dissociate that hydrate to understand the stability. So what we observed that when we actually look at surfactant and some of these other additives, then you can actually improve the stability of these hydrates in the subsea sediments. Some of these observations are also looked at in terms of how much hydrate water getting converted into hydrate in a percentage, and how much water getting converted into hydrate in the presence of surfactant. So this is a gas to hydrate conversion, this blue line, and this blue bar chart, and this yellow one represent the water to hydrate conversion. What we observed is that the surfactant did not improve the overall kinetics. They of course increases the rate of reaction, but the conversion is relatively lower than the simple bentonite condition. The reason behind that, what we observed, that surfactant tends to form foams, and therefore they inhibit the gas contact with the clay, and therefore the conversion observed to be slightly lower than the simple bentonite condition. These are some of the sample videos that how the hydrate looks like. So you can see that 1 weight percent bentonite in seawater and 7 weight percent bentonite in seawater shows slightly solid nature of the hydrate. However, when we use surfactant, then we observe that because of the foam, the hydrate that also getting formed is again very loose. So it's not that strong as like what hydrates are simply getting formed into the bentonite system. So though the surfactant may increase, the reaction rate, but they may not possibly have a strength into the hydrate. So some of these studies are very important to understand how the additives may impact the morphology of these hydrates. So in subsequent studies, what we actually looked at understanding the hydrate formation from liquid CO2, we carried out some rheological studies. So rheology or understanding the viscosity is also important, and we modified this conventional Cote geometry to actually form hydrates from a liquid CO2 or gaseous CO2, and then understand that how the hydrate formation occurs from gaseous or liquid CO2. So we actually modified this Cote geometry and had some kind of threads on that, so that you can actually have better mixing in the Cote geometry, and we consider conditions, primarily three conditions at this pressure 3.5 megapascal. One is a 5 megapascal and one is a 7 megapascal, and this condition represent gas and these two conditions represent liquid. So we studied the hydrate formation from gas phase and the liquid phase, both. So what we observed during this hydrate formation in this rheometer, that the pressure plays an important role. So look at this, the viscosity profile here. So these are the viscosity profile and these are the pressure profile. The solid line represent the pressure, and the dotted line represent the viscosity, corresponding viscosity. So this is a pressure 3.5 megapascal. So it starts decreasing and goes to about less than 2 megapascal in the rheometer, and the viscosity rises here. So you can see that viscosity is increasing. That indicates that hydrate formation is occurring into the rheometer. However, when you look at the higher pressure, which is about 6.5 megapascal, where the CO2 is in a liquid state, and so is the case for 5 megapascal, at this both the conditions, the hydrate formation is pronounced as compared to the lower pressure, which is, as I said, like sometimes may not be clearly visible in a simple reactor system. So you can see that, and this is again from pure gaseous and liquid CO2, so there are no clays that we used. And then one can see that there is a significant rise in the viscosity of the system that indicates the hydrate formation, and which is more than at lower pressure conditions. And then we also looked at the dissociation of this hydrate in the rheometer reactor assembly. And what we observed that at certain time, so when you try to dissociate that, hydrates in the reactor assembly, starting from about, increasing the temperature from about 277 degree Kelvin to about 285 degree Kelvin, there is a sudden rise in the viscosity at some point, which represent the point at which hydrate dissociates, right? So there's a sudden, increase in the viscosity that is primarily due to that hydrate crystals are trying to burst, and therefore the increases the state at that point. Also, there are some, hypotheses discussed in the literature which shows that, which tells that at that condition, possibly the hydrate crystals become more sticky, and therefore they provides more resistance near the equilibrium condition where the hydrate dissociates, and therefore there is a sudden rise in the viscosity observed. So in order to understand how this viscosity varies when you talk about CO2 sequestration into the subsea terrain, so we have carried out some studies using clay again, and using liquid CO2, and again understanding the viscosity variation. And we considered a pressure which is 5 megapascal and temperature about 277.15 Kelvin, and this is the point where it represents a liquid condition, and this is a CO2 phase diagram, and this is a CO2 hydrate in a seawater, and this is a CO2 hydrate in a pure water. So this condition represent hydrate formation from liquid CO2, and we carried out similar rheological studies in a rheometer, high pressure rheometer. And what we observed using clay, bentonite clay, and also the impact of promoter. This is a thermodynamic promoter that we use. This is a tetrahydrofuran. What we observed is that the THF do impact the hydrate formation phenomena, and that actually increases the hydrate formation rate, primarily because your conditions lies well within the hydrate formation zone. And what we observed is that there is a drastic rise in the viscosity at those conditions. Using this THF, what we also observed that, with certain tetrahydrofuran concentration, again, this is a sample additives that we use at the lab scale. Of course, more studies are required to understand their viability for ocean sequestration, but certain similar kind of additives can be explored for subsequent research. So what we observed that the yield stress when you use some of these additives to form hydrate help us to improve the yield stress of these hydrates. So therefore, yield stress represent the stress that is required to break these crystals, at that conditions of flow. So to make sure that your hydrates remain stable for long term, some of the hydrate formation studies can also be looked at using some of these additives to ensure that the hydrate that you are forming represent a more solid form at those oceanic conditions. So these are some of the snapshot of how the hydrate looks like, in a rheometer reactor assembly. One can see that how THF forms a very solid hydrates, which actually very sticky with the bob. And you can see here over here again, such kind of hydrates actually can be formed, and one can see that the gas is getting bubbled out. And these are conditions, not ice conditions. So these are primarily 277 degree K, close to 4 degrees centigrade, and about 5 megapascal pressure. So these studies are very important to ensure that hydrate formation is possible in seawater and the impact of some of these additives. We have also carried out some of the reactors some of the studies in the reactor. So we employed stirred reactor and porous bed reactor primarily to understand if you form hydrate XC2 at the surface and then inject that into the sea, how it looks like, and if you form hydrates either in the porous bed, which can be representative of subsea sediments, then how the hydrate formation will look like. So we carried out some of the studies, and some of the other promoters we have used, like sodium tripolyphosphate, tetrasodium pyrophosphate, and also we looked at pure water and seawater, and then we employed stirred tank reactor or porous bed reactor. And what we observed, at a certain pressure of 3.5 megapascal, these are sample pressure conditions that we used, and 274.65 Kelvin. What we observed is that porous bed reactor offers more hydrate conversion than the stirred tank reactor. Uh, some of the possible strategies for such studies is that either you can actually form hydrate XC2 using some of these promoters, and then sequester that hydrate as a molds on the sea floor. That is one way of looking at it. Or the other way is that you can actually sequester CO2 directly into the sediments using some of the strategies like horizontal well, and doing some of the small fracturing to inject CO2 along with some of these promoters, so that CO2 hydrates can be formed into the sediments. And again, as I said in a previous slide, that the sea depth will again define your stability, long-term stability. So it is expected that subsea sediments are some of the viable options to sequester large amount of CO2 into the ocean. So how this ocean pH may change, that is one of the questions that some of you might feel. So it has been reported in the literature, and then we have looked at that information. What we observed, that this is amount of CO2 stored, this is gigaton of CO2, and increase in delta P CO2 in parcel ppm. This is a green line over here, and this is a pH change. This increase in dissolved inorganic carbon, and the amount of gigaton of CO2 stored in entire ocean, this dotted blue line. What is represented is that if you inject CO2 into the ocean, compared to amount of CO2 stored in gigatons, look at this, numbers, 500,000 gigatons of CO2. So if you inject that, 500,000 gigatons, the pH may change by the unit minus 2.2. And this is again 200,000 gigatons of CO2. So at this point, again minus 2.2. And typically what we are trying to target is 1100 to 1500 gigatons of CO2. So this is close to somewhere here. So at this point, the amount of pH that the unit change may be very less, of the order of minus 5.5 or so. So the amount of CO2 that we propose to capture in near future, or sequester in near future, may not affect the pH as a whole in the sea. Of course, there might be a change locally in pH, and therefore more studies are required to understand the change of local pH conditions in the subsea sediments. So that's somewhere it paves the way for future research. So there are various possible storage sites that are proposed in the literature, and one can see that there are many storage sites that are possible at the sea coast. And again, the bathymetry will provide us more information at the depth, and then decides how the CO2 storage can be possible into the ocean for long-term stability. Of course, we need to understand overall, transportation cost of CO2, capture cost of CO2, and then how much penalty that is going to have overall strategies. However, we need to plan our power plants in a way that we can actually capture CO2 and store that into the geological formation. So there are some data that we looked at it. I will show that. But some of these possible CO2 storage classifications are possible in the ocean. So these are some of the types that we have proposed in literature: class 1, class 2, and class 3 types, where you can store CO2 into the sediments, where CO2 hydrate may form into the subsea sediments. That is a CO2 injection well. The other possibility that you can actually store CO2 into the hydrate at the sea floor, and that is where class 2 type of hydrate storage potential sites are there in the ocean. And there are class 3 types where you can actually store CO2 into the liquid pool, and then there might be a formation of thin hydrate crust which will store liquid CO2 for long term in a pool. Uh, the strategies to inject CO2 into the ocean could be many, and existing oil and gas procedures can be utilized, because oil and gas generally use some of these injection strategies for enhanced oil recovery and other purposes. Similar strategies can also be utilized to inject CO2 into the ocean. For example, you can have a vertical well, you can have a horizontal well injection into the sediments, you can have a multilateral well or fishbone injection that is possible in a subsea sediments. Then you can also store CO2 onto the sea floor using a ships. So offshore ships are also possible, where you can actually do subsea sediment, sea storage in the ocean in the form of hydrates and so on and so forth. So some of these strategies are possible, and one need to ensure that these remain stable for long term, and therefore more research is required at a field scale and understand the localized storage sites for long term storage. So what is the cost, so these are some of the cost that is expected in capture technologies. So most of the CO2 capture technologies are based on the adsorption or membrane based, and the cost varies depending upon the percentage recovery of CO2 from the flue gases and so on and so forth. It may vary from about close to $20 US dollar per ton of CO2 to about close to $80 per ton of CO2 in capture cost, depending upon the various data that we looked at in the literature. And then you also have to transport that, so you have to transport that by the ships, using ships or pipeline. So you can have an offshore pipeline and onshore pipeline. So some of this data is available for transportation cost US dollar per ton of CO2 with respect to the distance, 500 kilometer and 5,000 kilometers and so forth. And we can see that onshore pipeline, that is the data reported in 2005, and it is not again corrected with the inflation as on today, so it is used as it is. And one need to correct that with respect to today's inflation rate and so on and so forth. So this onshore pipeline and offshore pipeline are shown here, which is close to the offshore pipeline will add some more cost into the transportation, and you also have an onshore cost, and then you can also have a ship transportation shown here, which is of the order of $20 to $30 depending upon the distance. And again, you have offshore pipeline shown here by the red line as on 2020 data that we got from the literature. So the cost may vary about $30 per ton of CO2 depending upon the way we use either ships or pipeline. And then if you add that cost over here, then this is somewhere about say 60 plus 30, maybe 90. And there might be some additional cost that goes into injecting CO2 and some of the chemicals, operating cost, and that may add some possibly $30 to $50 of that order. So I expect that overall cost may go up to $150 per ton of CO2. Of course, some of the direct air capture technologies are being reported in the worldwide scenario. There are pilot plants available for direct air capture, and the costs are more, right? So this cost possibly is lower than some of the long-term DAC methods are being reported in the literature. And that's where I think overall picture of ocean storage into the subsea conditions. And with that, I thank many of our collaborators from industry, academia, and the institutes. And at the end of the day, I should thank my research scholars who are our backbone of the research at IIT Madras, and they are someone who help us to carry out good research, and I thanks them. And thanks to IIT Madras, a beautiful campus. I invite all of you to visit us, and that gives a good environment for research and academic activities. And I also thank American Chemical Society for inviting me for this talk, and I appreciate. Thank you so much.